Good evening, I'm Charles Schultz, and this is the Randomizer for the 9th of March 2022. And tonight's subject is TFT, thin film transistor. A thin film transistor is an interesting device that's made a little differently from other transistors. It has a lot of applications and it fits in places that others will not. We'll get into that very shortly here. Um, First of all, I want to welcome everybody who's participating tonight. I hope you're here with questions and thoughts, and we're going to share a little technology and a little knowledge with you. It's a lot of fun every time we do a randomizer. Every weeknight at 6 p.m. Eastern Standard Time, we have the randomizer with a random technical subject selected out of a pool of over 1,600 ideas. And on Mondays at 9 p.m. Eastern Standard Time, we generally have lessons running. We've done the Fermi Paradox series and we've done the Meta World series. We're moving on to some robotics and other ideas, other solar systems and their environments, life in space, and other things very soon. We'll be returning with our lessons in 2 weeks, and we'll have the schedule posted very shortly for that. Also, visit Universe Science Center and SchultzLaboratories.com. Go to the page, visit our links, and see how to sign up and become a supporting member. And also join our classes. Have fun with it. Bring your friends, take your Oculus, walk through our galleries, and explore some of the many exhibits and things we have. We're growing all the time, hoping to make this a major educational facility for people all over the world. So, thin film transistors. So, what's it all about? We talked a little bit yesterday about semiconductors, vacuum tubes versus transistors, solid state devices. And I pointed out that almost all solid state devices are grown on artificial crystals. Many of them made of silicon, some are made of other things such as gallium arsenide. Some are made with silicon on sapphire layers. There are many ways of doing it. But in every case, we make an artificial crystal that has the ability to donate electrons or have them moved around easily. So what a semiconductor is a device that's not quite an insulator and not quite a conductor, but it can be switched from one state to the other or somewhere in between. So imagine a material that with a minor amount of voltage applied to it changes its resistance or its ability to conduct very easily. Now, if you wonder what it's like, what is a transistor good for? I pointed out that amplification is one of the things that it can do very easily. A small amount of current or voltage applied to the control electrode, which is sometimes the base in a bipolar transistor, or just the gate in a MOSFET, a field effect transistor. When you apply a little voltage or a little current to it, it acts almost like opening the valve on a water faucet. You can control just how much flow there is. You can also imagine that if you had to stop the water coming out of your faucet or your hose with your thumb, there's usually about 60 or 70 pounds of force in there, and you just can't do it. So you have a little bit of leverage through the use of the faucet. And the faucet allows you to apply some graded amount of force to allow just a certain amount of water to flow, or to open it all the way and allow all of it to flow. So here's an interesting thought. The control voltage or the control current going to the base of a transistor is just about like how far you turn the knob on a water faucet. And in order for it to amplify, a weak signal is adjusting it on and off rapidly to allow the proper amount of voltage to emerge from the device. And that's how it amplifies a signal. A tiny whisper of a signal is the control to the faucet, and the gushing water going through is the resulting signal. Now, obviously, if you could go instantly from fully off to fully on, then that would be a switch. And many times we use transistors to switch things as well. So a thin film transistor is no different. It can do the same thing. So why do we need thin film transistors, and just what the heck are they? Well, it's found that very thin layers of certain materials can be induced into changing their resistance. And sometimes it's an exotic material like cadmium selenide or indium gallium zinc oxide. Some metal or alloy oxides work very well. Zinc oxide also works. That's the stuff that's the white you put on your nose to prevent sunburn sometimes, the sunburn cream. Well, it turns out that the idea is to have mobile electrons. So we talked about silicon, and germanium, which is very similar to it, are common materials used in making semiconductors. Some materials sometimes would have the right properties if you could get the right numbers of electrons, and 4 is just about ideal. So what if you don't have 4 electrons? Can you get around that? You can by creating a crystal out of mixed materials that have 3 electrons and 5 electrons, like gallium arsenide. Gallium on its own is just a metal, and arsenic is a nonmetal. But when you put them together, they donate 3 and 5 electrons to make an average of 4 apiece. So now you've created a crystal that has a previously unavailable sort of electron configuration. One of the great things about gallium arsenide is it's much higher temperature resistant. Some gallium arsenide chips run 300 or 400 degrees C or more before they'll burn out. And they also allow us to make extremely high temperature and high efficiency solar cells. But what's the deal with thin films? Well, it's found that many materials can be printed on a material or deposited on a material and turned into a transistor. Sometimes they will use organic semiconductors, or they will use even carbon nanotubes. And at this point, even a cardboard transistor has been invented. What are the advantages of the differences? Organic materials can actually be implanted in the body to do certain jobs, such as regulating the flow of drug from an implanted delivery system, with very little or no worry about toxicities. But many of the devices are used in very mundane products. Your cell phone, your flat screen TV, liquid crystal displays, all of them need conductors and switches in order to turn the pixels on and off to draw the graphics. So how does this work? Well, it turns out that many materials can be plated on a sheet of glass, for instance, very, very thin. And it turns out that many of these materials that are used in thin film transistors are optically transparent, so they will allow light to flow through them. Here's an electronic device that you can actually look through while it's in operation, and it doesn't seem to bother it in the least. So the idea of being able to put the electronic drivers and wiring on a plate of glass and then turn it into a liquid crystal display or a video display is pretty attractive, and the technologies to make that happen have been around for quite a while. For instance, there are many materials that can be put on glass that will conduct a little bit of current. It generally doesn't take a great deal of current to operate the individual pixels in a video display, and tin is a very good metal for that. So it was discovered a long time ago that you can plate tin metal directly on the surface of a sheet of glass and it becomes conductive on that face. This is also used for other things. If you have a whole network or grid of conductors on 2 spaced tin plates, you can actually move your finger over it and it will measure a change in capacitance, and it can locate where your finger is located. Or where the conductors overlap, you can put a dot of pixel material, liquid crystal or whatever, at each of those locations and use it to draw things like images, text, graphics. So this is a very popular method of creating these sorts of displays. Now, one of the interesting things is sometimes you need something a little more durable. And how do you make that happen? Well, it turns out you do a process known as deposition. Sometimes it can be done with a chemical vapor, or it can be done with metal that's being scanned with an electron beam and turned into a vapor and electrically deposited on the surface of a substrate. And generally, glass is a good material to use. Sometimes other materials are used. So you literally, just like the silver-covered sunglasses, can put a plate of material in a vacuum chamber, sputter metal onto it, coat it until it's silvery, and then etch away a pattern in it. Or you can do the pattern as you're doing the deposition. So there are many ways of doing it, but in the end, you end up with an electronic device, wiring and everything put on a flat display panel. Now that's pretty fascinating. Now, why in the world do we need, for instance, a paper transistor? I mentioned a little earlier somebody had actually invented one. Well, consider that it's possible to put displays literally in paper, and it's something that can be balled up and thrown away when you're done with it. For me, I would rather see something that you do use again and again, rather than having to go with discovering a new way of recycling a new and novel sort of material. On the other hand, there are many ways of doing things, and sometimes it's just the cheapest solution. Many years ago, when I was a kid, the backs of cereal boxes sometimes had a plastic record printed right on the box, and you could literally cut it out with scissors, put it on a record player, and this was the old mechanical ones with a needle, and play a bit of music or a song or a soundtrack off of it. So people have done some pretty strange things. If you go back a little further, Thomas Edison's original phonograph actually used a cylinder rather than a disc. And the cylinder would rotate, and a stylus would cut grooves in the wax surface, and the vibrations of sound would leave their mark. And when you played it back, that's how the sound was reproduced. It literally was shaking the needle that was amplified and made the sound. So a lot of people who like LPs or vinyl records are quite familiar with that technology. Anyway, I've been all over the map with this, but the fact is we found novel methods of making transistors that'll fit in extremely tight spaces and to do it very economically. Now, I figured they'd find a lot of uses for carbon nanotubes when they came up with them, but I didn't know they'd make transistors out of them. But when you think of it in retrospect, it makes a lot of sense. It's a material that has semiconductor properties that you can control. So just about anything can be used. Now, here's an exciting thing. There's a type of mineral that exists deep inside the crust of the Earth. It's not that often found on the surface, and it's down in the mantle as well. It's called perovskite. And perovskite comes in a couple of different varieties. The most common ones are based on magnesium metals or iron metal. And perovskites have very fascinating properties. We've studied the structures of them, the crystal structures, and been able to reproduce them on a flat substrate using some of the methods that I talked about. And one of them is to put a metal film on there and then apply a halogen to it, which could be chlorine or fluorine or bromine or some other halogen, and grow a perovskite film of this metal halide. And this mineral combination makes an unusually good thin film transistor. But perovskites also have another function showing up very soon. It's been discovered that they make pretty efficient solar cells, photovoltaic cells, for capturing the sunlight and turning it to electrical power. But inside the Earth, they've discovered something very interesting. When they did experiments with perovskites in what's called a diamond anvil cell, they were able to apply thousands or millions of pounds of force to the tiny crystal within, and they usually have to probe it with a laser or some sort of non-invasive method of measuring it. Well, you can run electrical contacts inside that cell, squeeze the crystal under 1,000,000 pounds or more pressure and heat it up, and that perovskite crystal takes on some very interesting properties. It can actually act as a superconductor in some ways. So for long times, many people wondered where the magnetic field of the Earth came from. Well, it turns out it may very well be caused by some of the effects of these perovskite crystals that, under compression and heat, can act as superconductors. So we've gone a long way from thin film transistors, but all of these bits and pieces do tie together. And it's interesting to know that the same sort of materials that you use to make your liquid crystal display on your calculator or the display on a cell phone can actually be related to the crystals of mineral deep inside the mantle of the Earth. So there are interesting connections all around us that many of us are never aware of. We never really think many times of where the plastic comes from, or the metal comes from, or where any of the semiconductors come from. And if you knew the whole story, it probably would be long and tiring, but for some it would be a fascinating bit of history and information. And for me, I'm interested in all sorts of things like that. So thin film transistors have been very revolutionary in that they've allowed us to make displays that are fully transparent, and today you actually can find televisions that are not mounted in a frame, but are literally as thin as a sheet of paper or a little thicker and can be flexed, and you can look through them. I've seen a couple of projects online where you disassemble a flat panel TV and mount the resulting device on a sheet of glass so that you can see right through your television display. And I've seen in some of the stores, the technical stores in Japan, they've been using that to produce false hologram displays so that the windows literally light up with video built right into the glass or right on the surface of the glass. So interesting times, and I can guarantee you that with the advances we're making today in technologies such as thin films, we're going to see some really interesting displays and other things show up. Who knows where it'll lead? So now at this point, if we have anyone who has any questions or ideas, the floor is open, and I will sit here and wait to see a text pop up or a voice pop up on the microphone, and I'll take that question live. And by the way, do go to schultzlaboratories.com or universesciencecenter.com. Visit our galleries, play around. I am going to be answering a lot of questions also live from some of those galleries as soon as I get that capability programmed in. It'll be a lot of fun then too. It'll be like a Zoom meeting but in 3D. And let's hope that we can get enough supporters so that we can double and triple the size of the facility and add a lot more interesting things. Pretty soon you'll be building and launching rockets in there, smashing planets together, and doing a lot of other outrageous things. And one of my favorite rooms that I'm working on is the magnitude room. In that room, you'll be able to shrink down one order of magnitude at a time until you get smaller and smaller down to the scale of atoms and even smaller than the particles. So it's going to be a long road, but we're working on all those components, and hopefully we'll have some more to show you very soon. Well, I don't have any questions and I don't have any suggestions here on the floor, so I'm going to close after reading my quote for the day, and I hope this is a little inspirational to people. It is, "Hope deferred makes the heart sick, but when the desire comes, it is a tree of life." And that's from Proverbs 13:12. So I know a lot of us get really disappointed waiting for something to occur, but when it finally does, it's a major victory for us one way or another. So keep the faith. And just remember, things can always be much worse. It's up to us to make them much better. So everybody have a wonderful evening. Thank you for joining me tonight here with the Randomizer. Tune in tomorrow for another technical term. We'll do something more interesting, perhaps. It'll always be fun. So everybody have a wonderful evening, and of course, make the world a better place. I'm Charles Schultz, and thank you for listening.